Hi everyone, we are from Section 3 Group A. Our group consists of me, Emily, Dong Chiyan, T. Chi Huang, and Clara. Today we are going to present our flash separator design.
So before starting the project, we need to understand what is flash separator. So a flash separator is an industry equipment used to separate liquid and vapor phase in a mixture by rapidly reducing the pressure. So this causes the vapor phase to evaporate flash while the remaining liquid phase is separated. The purpose of a flash separator is to recover valuable volatile components from the mixture or to prepare the liquid phases for further treatment. So here is a picture of layout of flash separator. We can see that the vapor with lower density will flow to the higher outlet, which is vapor outlet, and the liquid with lower density will flow into the bottom outlet, which is liquid outlet. So the objective of this project is to first design a flash for separating a mixture of methanol and water. Secondly is to review the process and typical process conditions such as overall composition, operating pressure and temperature for the separating of the binary mixture. And third is to calculate the mole of liquid, mole of vapor, liquid phase mole fraction, and vapor phase mole fraction.
For the first step of calculation is to state assumption and determine overall composition, operating pressure and temperature. So for assumption, we assume that our mixture is an ideal solution and our basis is equal to 1 mole of feed. So for condition of specific, we let our operating temperature equals to 80 degrees Celsius. To be noted that the boiling point of methanol and water are 64.7 degrees Celsius and 100 degrees Celsius. To ensure effective separation, the operating temperature must be set between the normal boiling point of these two components. Therefore, we select 80 degrees Celsius as the operating temperature for our flash separator. So for pressure, we set 180 m, and for mole fraction of methanol and water are 0.6 and 0.4.
Let's proceed with step 2, calculate the moles of liquid, moles of vapor, liquid phase mole fraction, and vapor phase mole fraction. To calculate the saturation pressure for methanol and water, we use the Antoine equation. The value A, B, and C for the Antoine equation are obtained from table B2. By using the equation in the previous slide, we can calculate that the saturation pressure for methanol is 179.6685 kilopascal and the saturation pressure for water is 47.4441 kilopascal. Next, we calculate the bubble point pressure and dew point pressure. For the bubble point pressure, we use the equation P bulk equals to x1 times P saturation 1 plus x2 times P saturation 2, and we will obtain the value of 126.7787 kilopascal. For dew point pressure, we use the formula 1 over Y1 over P saturation 1 plus Y2 over P saturation 2, and we will get the value of 84.9585 kilopascal. Moving on, we calculate the equilibrium ratio K by using the formula saturation pressure over pressure. For methanol, we obtain the value of 1.7732, and as for water, we obtain 0.4682. Now we can calculate the liquid phase mole fraction X. To calculate the mole fraction for methanol, we use the equation pressure minus saturation pressure 2 over saturation pressure 1 minus saturation pressure 2, and we obtain the value 0.4075 mole methanol per mole. For x2, we simply use the equation 1 minus x1, and we obtain the value of 0.5925 mole water per mole. To calculate the vapor phase mole fraction y1, we use the equation liquid phase mole fraction x1 times the equilibrium ratio k1, and we obtain the value of 0.7223 mole methanol per mole. To find the vapor phase mole fraction for water, we use the equation 1 minus y1, and we get 0.2777 mole water per mole. To calculate the moles of vapor V, we use the equation summation of Z times K over 1 plus V times K minus 1 is equal to 1. And the value we obtain for moles of vapor is 0.6109 mole. To calculate the moles of liquid, L, we use the equation 1 minus V and we obtain the value of 0.3891 mole.
So the final part is the conclusion. Flash separation is a fundamental concept in chemical engineering, enabling the efficient separation of mixtures like methanol-water by leveraging differences in volatility. In this project, a methanol-water mixture was separated in a flash separator operating at 80 degrees Celsius and 1 atm. Through calculations, we determined the system produces 0.6109 moles of vapor and 0.3891 moles of liquid from 1 mole of feed. The vapor phase composition showed significant enrichment of methanol with a mole fraction of 0.7223, while the liquid phase was richer in water at 0.5925 mole fraction. These results validate the assumption of ideal solution behavior and highlight the practical applicability of Antoine's equation, Raoult's law, and mass balances in real-world design. Ultimately, this project reinforces the importance of thermodynamic modeling in optimizing chemical separation units for both efficiency and product equality.
That is the end of this video. Thank you for watching and have a good day.